Hello! In our most recent Further Maths tutorial video, we introduced the idea of polar coordinates, and therefore today we're building upon that by showing how you can convert between polar coordinates and the traditional Cartesian x and y sort of equations you're used to seeing before. So let's get stuck into that by starting by showing how to convert from Cartesian to polar, because out of the two conversions you can do, that's the easier way around to do it. So how do we do this? Well, we're going to need to know some formulas to help us do those conversions, and it's easy if you do just remember those formulas off by heart. However, even if you can't remember them off by heart, that's not an excuse to not be able to do these questions, because to be honest, the formulas are very intuitive. They all just come from the diagram that basically explains the definitions of what r and theta are in the first place. R, of course, is the length from our point to what used to be called the origin, is now officially called the pole when we're talking about polar coordinates. And then theta is a measurement of how far you have to rotate anti-clockwise from what used to be called the positive x-axis and now we call the initial line. Because if we do that in the way that you can see on the screen right now, it forms, what do you know, a right angled triangle, which is great because we know so much maths to do with right angled triangles now. For instance, of course, the classic trigonometry, because r, of course, is the hypotenuse, y is the side opposite the angle, so therefore we can say that y must equal r sine theta. Similarly, x is the adjacent, so therefore we know that x must equal r cos theta as well. And therefore, between those two equations, it's possible to replace all the y's and x's in your Cartesian equation to write them in terms of the two polar variables of r and theta. However, there is a third equation to help you convert things that is very helpful and quick to use in certain scenarios, and this is obtained using Pythagoras. Of course, by Pythagoras, x squared plus y squared must equal r squared, and that's very useful because it means instead of having to individually convert the x's and y's if they're in that particular structure, you can just instantly replace them both with an r squared together. So therefore, let's put that into practice. Let's convert these Cartesian equations into polar equations. The first one, what do you know? We've got that x squared plus y squared structure, so we can just instantly rewrite it as r squared equals 16. Now, that equation is in polar form already now, but something we do like to do with polar equations is we prefer most of the time to write them in the form r equals, in a similar way to how we often like to rewrite Cartesian equations when we can in the format y equals, just because it's nicer to deal with when they're in that format. Normally, the questions will be clear, though, in terms of what format they want you to leave the final answer, just because otherwise the question is very open-ended in terms of the number of different formats you can leave it in. Anyway, for us, we're going to rewrite these in the form r equals, and so for the first one here, we could square root both sides. And that will get us r equals 4. Some of you might be a bit worried that in doing so, I've not put a plus minus 4 there, and therefore it appears like I might be losing a bit of the graph, because it's always risky to just square root both sides of an equation without putting a plus minus, except because this is polar coordinates, we know we're dealing with that convention of r is greater than 0 a lot of the time. So therefore, as r equals minus 4 is a bunch of points that only involve r with negative values, we don't really care about that bit of the graph anyway. So therefore, that's why I'm able to just write it as r equals 4. And then the other aspect is this equation makes complete sense if you think about it, because the original equation was, of course, a circle with center 0, 0 and a radius of 4. And r equals 4 is describing a bunch of points that are all a distance of 4 away from what used to be called the origin, which is just a wordy way of describing a circle effectively. So there you go, first question done. Only little side note to mention there, though, is that technically this was the quick way of doing it, but if you'd forgotten the quick way, even if you did it the long way, it would still work out absolutely fine, because all you'd have to do is replace the x with r cos theta. Then, of course, realizing that it's x squared, so we're going to square it. Y is r sine theta, and then it's y squared, so we're squaring that. That's equal to 16. Applying index laws means we can square the individual things there. So r squared cos squared theta plus r squared sine squared theta. We can then factorize r squared out of both those terms. And then we notice inside the brackets, we've got a sine squared theta plus a cos squared theta. And oh, what do you know? It's that classic trig identity again. So therefore, we just get r squared equals 16, and therefore r equals 4 again. So you can see that even if you go the long way, you'll still get the correct answer. Better if you do remember the shorter way, but it doesn't stop you from being able to get there eventually. Going into the second question, but going through it a bit more quickly, it's the same idea. Replace the y and the x with their individual conversions, because there's no quick way, because there isn't an x squared plus y squared situation going on there. So we have our sine theta, we have our cos theta, all squared. We're squaring that. And then we're being aware that we want to get it in the form r equals, and therefore the easiest way to do that would be to divide both sides by r. Now, normally that's very risky to do because we're dividing both sides by r with the intention of cancelling out an r on both sides. And you might have noticed that in some other videos I made a big point about how that's a risky idea. The reason I'm allowed to do it in this case, though, is just because if I divide both sides by r, what I'm effectively losing is the part of the equation that says r equals 0. Because if I was to move everything onto one side and factorize, r equals 0 is what you get out of that. But the thing about r equals 0 is it's literally just a single point. It's effectively just the origin. And therefore, we're not so concerned about losing that, because being just a single point, the chances are, because our original graph didn't just have the origin as its own separate floating point, it was just part of the rest of the graph. Therefore, actually, the rest of the algebra should include that point anyway. So actually, having that r equals 0, or that extra factor of r everywhere, was just effectively double accounting for the origin. So getting rid of that extra r is not a problem. So then all I need to do is divide both sides by cos squared, and therefore r is equal to sine theta over cos squared theta. There you go. And that is a polar equation. Admittedly, of course, be aware, sometimes in these questions you need to use trig identities to rewrite things. For instance, it's worth pointing out this particular question could be rewritten. I wouldn't have had to, because again, this question didn't ask me to, but you could realize this could be rewritten as sine theta over cos theta times by 1 over cos theta, and then therefore that's the same as tan theta sec theta. So always be on the lookout for having to manipulate your trig functions, particularly in questions that show that, because they, are telling you what you need to head towards, so you're aware you might need to do some extra manipulation to get there. Nice. Okay, so that's going from Cartesian to polar. What happens if you're going the other way around? What happens if you're converting from polar equations to Cartesian equations? Well, the simple answer initially would be to just say, well, we can just use those same conversions already. If you've got an r squared, replace it with x squared plus y squared. If you've got an r times a sine theta, you can just instantly replace it with a y. And if you've got an r cos theta, just instantly replace it with an x. The problem is, a lot of polar equations don't have these things conveniently just sitting there in this structure. So therefore, that is where we also have to be aware of some other conversions we sometimes have to do. These are the conversions that are always your top priority, because they're a way of just instantly converting to a very nice expression in terms of x and y. Whereas some of these other conversions I'm going to be showing you are ones that are best avoided if you can, because they're more horrible to deal with and are sometimes even just an imperfect way of actually representing the original polar equation as a Cartesian equation. However, there is also a fourth nice conversion I'd want to add to this list that we currently have on the screen, which is if you do that second equation, r sine theta, divided by that third equation, r cos theta, the r's will technically cancel out on both sides, and therefore you find that tan theta can just instantly be replaced with y over x. So again, it's a bit niche, because you're not going to have just a tan theta floating there every single time, but if you see a tan theta floating there, you can just instantly replace it with y over x. That's quite nice. Then there are some other conversions you can do, though, in case you don't have any of these very nice situations just instantly appearing there to be instantly replaced. One of the next things you might want to try is a more simple rearrangement of these two conversions, because both of these could be rearranged to make the trig function the subject of the formula. For instance, you could replace sine theta with y over r. Now, as I've already said, this is a less preferable conversion than the other ones we've already said, because we're replacing theta, which is good, that's one the polar variable's gone, but we're replacing it in terms of a thing that still has another different polar variable in. But the thing we can do is we can still just replace all the sine thetas and cos thetas because they involve trig functions that are more annoying, and then later gather any remaining r's together and then use our top conversion to try and then replace any remaining r's. Similarly, cos theta equals x over r, and so therefore those are kind of like your second priority, and you can probably hopefully see why. I wouldn't remember off by heart, there's a sort of tier list. It just makes sense logically why these are not as good conversions as the other ones. And then there's also almost arguably a third tier of even worse conversions that sometimes you are forced to use because you don't have any of these nice expressions that you can see so far appearing in your equation, but you want to avoid using these more horrible expressions because they are just more horrible, either because they look more horrible, they make the equation more problematic to deal with, or sometimes actually just because they don't properly convert everything that the original polar graph was doing. So what are they? The first one we can have is if we try to rearrange that top conversion of r squared equals x squared plus y squared into a conversion that allows us to just replace the r equals. And therefore, to do that, we square root both sides, and therefore we know that if you want to replace an r, you can technically replace it with r equals the square root of x squared plus y squared. Doesn't look very nice, but it technically works. Cool, so that's one conversion, and then there is one more conversion, or kind of one more set of conversions. What happens if a theta is not inside a trig function? Well, we can start to rearrange any of those trig things we've already used, any of these trig conversions we've already written, to make them theta equals. For instance, the tan theta equals y over x, we can rearrange that to make that theta equals by using arctan. So technically, theta could be replaced with arctan of y over x. Do you want to do that if you can avoid it? Well, no, because arctan is an imperfect way of undoing tan, so some of the graph is sometimes lost by doing this, as well as arctan itself being a bit of the pain, just like arcsine and arccos are also problematic to use. So yes, technically you could have arcsine of y over r and then replace r with square root of x squared plus y squared. Of course, that's also even more horrible, but if you're in a bit of a bind, you can use them. Cool. So let's use these and put them into practice. So we've got this first question right here. R equals 12 sec theta. Oh my goodness, how are we going to convert it? You might be tempted to instantly resort to those worst case scenarios of using r as the square of x squared plus y squared and trying to replace the theta in sec theta with theta equals arctan of y over x. But no, don't rush into using them. See if there's ways you can use those nicer conversions first. And what do you know? There is, because sec theta is 1 over cos theta, which means there is a way I can rearrange this to make the r being multiplied by a cos theta. And the reason I want to do that is because we know that r cos theta can simply just be replaced with x. And so therefore this is actually a very nice equation indeed. It's just a straight line, a vertical straight line of x equals 12. Just obviously passing through the x-axis at x equals 12. So very nice equation. No need to involve any inverse trig. So just be aware, you're always on the lookout of ways to convert these nicely if you can. And then moving on to our second equation. Of course, again, very tempting to just replace r instantly with the square root of x squared plus y squared. But if we can avoid it, we'll prefer not to. So we'll wait and we won't do that conversion first because we can see there's a nicer conversion to start with. We can see there's a tan theta involved. Therefore, that's a great starting point. So we'll start by replacing tan theta with y over x. We can also see that sine squared theta there. Not the nicest conversion in the world, but also not the worst level, because we said that sine theta is equal to y over r. So therefore, sine squared theta is equal to y over r squared. Then we can do some more rewriting. Of course, we can be aware that we can multiply the brackets, and therefore we'll end up with, on the bottom, y cubed over xr squared. Of course, then you can flip that fraction upside down because it's a 1 over. So therefore we've got x squared, or sorry, not x squared, just xr squared all over y cubed. And then if we go all the way up here, try and cram it in on this page, then we can realize that actually the x and the y cubes we're going to leave alone for the moment, but the r squared is inside a square root, so we could now actually decide to factorize that out, because we'll realize it's therefore going to be the square root of x over y cubed, square of r squared. And that's good because it means we've got an r on both sides, which once again we can cancel out. So we never needed to use the square root of x squared plus y squared, because just there's an r on both sides, and we can just get rid of it before we even needed to do the conversion. So therefore, we end up with this. We could then get rid of the square root by squaring both sides. Remember, that's normally allowable to do to an equation if there is a square root involved that you're trying to undo. We could times both sides by y cubed. And then we could cube root both sides. Cube root is a much safer action to do than square rooting, so I'm less scared of doing that as an operation. But therefore, we get the equation y equals the cube root of x, or y equals x to the power of a third. And then, boom, we have converted our polar equation into a Cartesian equation. Okay, there you go. That is how you can convert between polar and Cartesian. There are those conversions you need to know, preferably off by heart, but even if you can't remember them off by heart, you can derive them. Going from polar to Cartesian is more fiddly, but there are those extra conversions you can use. But to know which ones you should be or shouldn't be using is kind of fairly obvious. Just by looking at them, you're wanting to avoid the ones that look more nasty, which makes sense. So with all that said, that will do for today. See you in a future video. Goodbye.